There is an object in our galaxy right now. You cannot see it with the naked eye. You cannot point to it on a star chart and say, there, that bright one, that is the one I mean. It is invisible. It is silent. From a distance, it looks like nothing at all. And yet this object, this invisible, unremarkable-looking point in the dark, is among the most extreme things that has ever existed in the history of the universe. It is smaller than London. If you placed it on the southeastern coast of England, it would not reach the M25 motorway. You could drive across it in the time it takes to finish a cup of coffee, and yet it weighs more than the sun. All of the sun's mass, 333,000 times the mass of the Earth, 2 octillion tons of hydrogen and helium fused over 5 billion years, compressed into a sphere you could see from an aeroplane window. The density is beyond all intuition. Take a single sugar cube, the kind you might drop into your morning tea, and fill it with the material from this object. That cube would weigh 100 million tons, more than the weight of every building, every bridge, every road, every car and ship and aircraft ever constructed in the entire history of human civilization, from one sugar cube. The gravity on its surface is 200 billion times stronger than the gravity holding you to the Earth right now. If you were somehow transported there, if you could survive the journey, which you couldn't, the tidal forces between your head and your feet would be so extreme that you would be stretched into a thread of atoms before you even landed. You would not be crushed, you would simply cease to exist as organized matter. The temperature of its newborn surface reaches 10 million degrees Celsius, hotter than the core of the sun itself. It spins. Oh, does it spin? Some of these objects complete a full rotation more than 700 times every single second. The equator of such a star moves at nearly 1/5 of the speed of light. At these rotation rates, if it were any larger, it would tear itself apart under its own centrifugal force. It exists at the absolute physical limit of what rotation can sustain. And every rotation, every single one of those 700 spins per second, it sweeps a beam of radiation across the cosmos like an impossibly fast lighthouse, a pulse, a tick, a heartbeat of pure physics. We call these objects neutron stars. For decades after their discovery, we treated them as curiosities. Exotic, yes, extreme, certainly, but understood, we thought. Cataloged and explained. We were profoundly, fundamentally wrong. Because in the past 20 years, and especially in the past decade, neutron stars have revealed themselves to be something far stranger than anyone imagined. They have shown us matter behaving in ways our equations cannot fully describe. They have produced energetic events that ionized Earth's own atmosphere from 50,000 light-years away. They have collided, producing ripples in the fabric of space-time and raining gold across a galaxy. They have sent us signals from billions of light-years away that we still cannot completely explain. And at their cores, buried beneath kilometers of the densest matter in the observable universe, there may exist a state of matter that has not been seen freely since the universe was 1 microsecond old. This is not a story about a simple dead star. This is a story about the limits of physics itself, about what happens to matter, to reality, when it is pushed beyond every threshold we know, about what the universe becomes when all the comfortable rules break down. In the next 3 hours, we will follow the evidence. From a young graduate student's chart recorder twitching in a field outside Cambridge to the collision of 2 dead stars 130 million light-years away. From laboratories deep underground to radio telescopes spread across continents. From the birth of the universe itself to its cold, dark, inconceivably distant death. Today, we journey through evidence that challenges everything we thought we knew about matter, about space, and about the universe we inhabit. Prepare yourselves. We begin.
It is the summer of 1967. The world outside is turbulent. Student protests, the Vietnam War, the summer of love. But in a field near Cambridge, England, the noise of the world is irrelevant. Here, in the flat agricultural land of Mullard Radio Astronomy Observatory, what matters is the noise of the universe. A 24-year-old PhD student named Jocelyn Bell has spent months helping to build a radio telescope. It is not like the iconic dish antennas you might picture. It is a forest of wooden posts and wire covering an area equivalent to 57 tennis courts, designed to track quasars, distant brilliant cores of galaxies powered by supermassive black holes. Bell's task in the months following the telescope's activation is both critical and deeply unglamorous. She reads the data, by hand, on paper. Every day, the telescope produces roughly 30 meters of paper chart, a continuous readout of radio signal strength against time. Bell's job is to crawl through this output, hundreds of meters of it per week, distinguishing genuine cosmic signals from terrestrial interference, aircraft, car ignition systems, malfunctioning electrical equipment. It requires patience, a sharp eye, and an intimate familiarity with what ordinary interference looks like. In August 1967, Bell notices something, a small, regular, repeating signal. She marks it, just a note in the margin, a flag for later review. It is unusual. It doesn't look like interference, but it also doesn't look quite like anything else she has seen. She calls it scruff. Weeks pass, the signal reappears, always from the same patch of sky, always with the same spacing between pulses. Bell brings it to the attention of her PhD supervisor, Anthony Hewish, one of the leaders of the project. They set up a faster chart recorder to capture the signal in finer detail. On November 28, 1967, it runs for the first time on the mysterious source. The output is unambiguous. The signal pulses with extraordinary regularity. Every 1.3373 seconds, exactly, a burst of radio energy arrives from a fixed point in the constellation Vulpecula. 1.3373 seconds every single time, not approximately, not roughly, exactly. This precision is deeply, deeply unsettling. Natural astrophysical phenomena, gas clouds, variable stars, galaxies, do not behave this way. They don't produce repeating pulses timed to the millisecond. Only one kind of source in human experience produces signals this regular, an artificial transmitter, an engineered beacon. Bell and Hewish named it with a half-joking designation, half-serious in its implications, LGM-1, Little Green Men 1. They are serious enough about the possibility of an extraterrestrial civilization that they briefly consider not publishing, worried about the geopolitical implications of announcing possible contact with an extraterrestrial civilization, and equally worried about embarrassment if they are wrong. Hewish later described the atmosphere in the observatory as quietly tense. Nobody openly discussed the alien hypothesis. Nobody needed to. It was the obvious possibility that no one would say out loud. But over the following weeks, the case for an artificial origin collapsed. Further analysis showed the signal exhibited a subtle dispersion. The radio waves at slightly different frequencies arrived at slightly different times in a pattern consistent with the signal having traveled through the interstellar medium, the thin plasma of ionized gas between stars. This is a property of a signal originating far outside our solar system. An artificial beacon in our solar neighborhood wouldn't show this. More significantly, in January 1968, Bell discovered 3 more similar pulsing sources in different parts of the sky. Then a 4th. Whatever these things were, there were many of them. The universe was not populated by multiple alien civilizations, all choosing to beam the same kind of signal at Earth.
These were natural objects, objects unlike anything previously known. They were eventually named pulsars, pulsating radio sources, and the explanation for their extraordinary clockwork precision would turn out to be stranger and more wonderful than any alien beacon. A pulsar is a rapidly rotating neutron star. Its magnetic poles, which, like Earth's, are not perfectly aligned with its rotation axis, emit tight beams of radio energy. As the star rotates, those beams sweep around like a lighthouse. If Earth happens to lie in the path of one of those beams, we receive a pulse of radio energy once per rotation. The reason pulsars are so extraordinarily regular is that rotating neutron stars are in effect the most stable spinning objects in the universe. They are not burning fuel that could cause them to wobble. They are not convecting or pulsating like ordinary stars. They are simply spinning, dense, rigid, stable, and they slow down so imperceptibly slowly that over human timescales, their rotation is essentially constant. The most stable millisecond pulsars keep time so accurately that they are used to verify and calibrate atomic clocks. Bell's discovery earned a Nobel Prize in Physics in 1974. Controversially, and this controversy has never fully died, the prize was awarded to Anthony Hewish and radio astronomer Martin Ryle, not to Jocelyn Bell, who made the actual discovery. The Nobel Committee's reasoning that the prize recognized the development of the telescope and the observational technique rather than the individual detection was widely criticized by the scientific community. Sir Fred Hoyle, the famous British cosmologist, called the decision scandalous in public. Jocelyn Bell Burnell, she later took the name Burnell after marriage, has handled this injustice with extraordinary grace and generosity over the subsequent decades. When she was finally awarded the Breakthrough Prize in 2018, $3 million, one of the largest prizes in academic science, she donated the entire sum to the Institute of Physics to fund PhD scholarships for students from underrepresented groups. She said, characteristically, that she thought the money could do more good elsewhere than it could sitting in her bank account. The work, she has always maintained, was the reward. And the work, Bell's discovery, cracked open a door that 5 decades of subsequent science has been walking through ever since.
To understand what Bell discovered, we need to understand what a neutron star is. And to understand that, we need to watch a star die. Not just any star. Our sun, when it eventually runs out of fuel in about 5 billion years, will not produce a neutron star. It is not massive enough. The sun will swell into a red giant, shed its outer layers as a beautiful planetary nebula, a shell of glowing gas expanding slowly into space, and leave behind a white dwarf, a dense, cooling ember of carbon and oxygen, roughly the size of the Earth, sustained against gravity by a quantum mechanical phenomenon called electron degeneracy pressure. That is a peaceful death, as stellar deaths go. But imagine a star with 15, 20, 30 times the mass of the Sun, a blue supergiant burning at temperatures of 30 or 40,000 degrees at its surface, 10 times hotter than the Sun on the outside and incomparably hotter within. These stars are profligate with their fuel. They burn so hot, under such extreme internal pressure, that they exhaust their hydrogen supply not in 10 billion years like the Sun, but in 10 million. They are the rock stars of the stellar world, brilliant, extravagant, and short-lived. The life of a massive star is a story of nuclear fusion advancing through the periodic table. In the core, hydrogen fuses into helium. When the hydrogen in the core is exhausted, the core contracts and heats until helium ignites, fusing into carbon. Carbon fuses into oxygen, oxygen into neon, neon into magnesium, magnesium into silicon. The star becomes a layered structure, like an onion, with each shell burning a different fuel, and the ash of each layer becoming the fuel for the next one inward. All the while, the fundamental bargain of the star's existence is maintained. The energy released by nuclear fusion pushes outward against gravity, and gravity pulls inward against the fusion pressure, and they hold each other in equilibrium. This balance, gravity versus fusion, is what a star is, and eventually, inevitably, it fails. At the center of the star, after all the intermediate fuels are consumed, sits a growing core of iron, and iron is special. Iron is, in a sense, the end of the road for nuclear fusion. When you fuse lighter elements together, hydrogen to helium, carbon to oxygen, you release energy because the products are in a lower energy state than the reactants. The energy has to go somewhere, and it goes into the light and heat that makes stars shine. But iron is different. Iron sits at the absolute bottom of the nuclear energy landscape. It is already as stable as a nucleus can be. If you try to fuse iron into heavier elements, the reaction doesn't release energy, it absorbs it. Iron fusion robs energy from its surroundings rather than providing it. So when the silicon shell finishes burning and the iron core reaches a critical mass, approximately 1.4 times the mass of the Sun, a threshold known as the Chandrasekhar limit, something catastrophic happens. The support disappears. The iron core, no longer receiving energy from fusion and no longer supported by electron degeneracy pressure, begins to collapse. And when I say collapse, I want you to understand the timescales involved. We are not talking about a slow, gradual process that happens over thousands of years. We are talking about a collapse that takes less than 1 second. In approximately half a second, the iron core, initially roughly the size of the Earth, collapses to a sphere roughly 20 kilometers across. The density goes from several 100,000 grams per cubic centimeter to hundreds of millions of tons per cubic centimeter. The collapse accelerates from rest to 1/4 of the speed of light in under a second. During this collapse, something fundamental happens to matter itself. The electrons, which in ordinary matter have a kind of quantum mechanical stubbornness that resists compression, are squeezed with such force that they combine with protons. Electron plus proton becomes neutron plus neutrino. In an instant, vast numbers of electrons and protons are converted into neutrons, and a flood of neutrinos, nearly massless, nearly non-interacting particles, is released. In that half-second of core collapse, the newborn neutron star radiates more energy in neutrinos than the Sun will radiate in light over its entire 10 billion-year lifetime. The neutrino burst from a supernova in the nearby galaxy, the Large Magellanic Cloud, was actually detected by underground neutrino detectors on Earth in 1987, the first time we had ever directly detected neutrinos from beyond our solar system. But back to the collapse. The core reaches nuclear density, the density of an atomic nucleus, and the neutrons resist further compression through a force called neutron degeneracy pressure. The core stops collapsing almost instantaneously. It is as if the entire core has hit a wall. The collapse halts so abruptly that the core actually bounces. The outer layers of the star, which have been falling inward at a significant fraction of the speed of light, slam into this newly stiffened core and rebound outward. The shock wave propagates through the infalling material. What follows is one of the most energetic events in the universe, a core collapse supernova. The outer layers of the star are blasted away with energies equivalent to approximately 1 followed by 44 zeros joules. That is a 1 followed by 44 zeros. To put this in some kind of human context, all the energy the Sun has ever radiated in its entire 5 billion-year existence represents about 1% of the energy released by a core collapse supernova. The supernova briefly outshines the entire galaxy in which it occurs. The outer star is gone, expanding outward as a beautiful, violent nebula of gas and dust. What remains at the center is the collapsed core, the neutron star, a sphere of pure neutrons, 20 kilometers across, more than a solar mass, spinning because the collapsing core conserves angular momentum, just like an ice skater who spins faster when she pulls her arms in. A core that was rotating slowly over thousands of kilometers is now rotating rapidly over 20 kilometers. Some neutron stars are born spinning dozens of times per second. Some, in particularly violent collapses, are born spinning hundreds of times per second. The magnetic field is similarly amplified. A star that had a modest magnetic field has compressed that field into a much smaller volume, intensifying it by many orders of magnitude. The newborn neutron star is extraordinarily hot. Temperatures in the core reach hundreds of billions of degrees Celsius. Massive amounts of energy are lost to neutrinos in the first 10 seconds, cooling the core rapidly. But the surface remains at millions of degrees for thousands of years, hot enough to glow brilliantly in X-rays. This is what Jocelyn Bell discovered. Not the light of a living star, but the radio heartbeat of a dead one. A spinning ball of neutrons the size of a city, sweeping its radio beam across the cosmos, announcing its existence with metronomic precision. And it is extraordinary, genuinely extraordinary, that something so violent, so catastrophic, so extreme should produce something so regular. The universe took the most explosive stellar event possible and left behind the most precise natural clock possible. That irony has not been lost on physicists.
I want to spend a moment trying to truly convey what we mean when we talk about neutron star density, because the numbers are so extreme that they become meaningless without some effort at context. The most useful comparison starts with familiar matter. The densest naturally occurring element on Earth is osmium. A cubic meter of osmium weighs about 22,590 kilograms, roughly 22.5 tons per cubic meter. It is famously heavy stuff. You would not want to drop a cube of it on your foot. The core of the Sun is far denser, about 150 grams per cubic centimeter, roughly 7 times the density of osmium. But it is still ordinary plasma, protons and electrons bouncing around in an ionized gas, just very tightly packed. A white dwarf, the remains of a sun-like star, is denser still. A cubic centimeter of white dwarf material weighs roughly a ton. If you scooped out a teaspoon of white dwarf matter and brought it to Earth, it would be heavy enough to punch straight through the floor of whatever building you brought it into. A cubic centimeter of neutron star material weighs approximately 400 million tons. Not 1 ton, 400 million tons per cubic centimeter. To match the mass of a single cubic centimeter of neutron star, you would need to gather together roughly 67 million elephants. You would need to completely disassemble and compress roughly 55,000 of the Great Pyramids of Giza. You would need to take the entire annual grain harvest of the entire world and multiply it by about 1,000 from a single cubic centimeter. Or think about it this way. Mount Everest weighs approximately 810 trillion tons. A neutron star with a radius of 12 kilometers has a volume of about 7,238 cubic kilometers. At 400 million tons per cubic centimeter, the total mass of that neutron star would be equivalent to roughly 3.5 million Mount Everests. That is what is sitting in a sphere the size of a city. The surface gravity is equally mind-bending. On the surface of the Earth, gravity accelerates you downward at 9.8 meters per second squared. On the surface of the Sun, it is 274 meters per second squared. On a neutron star, surface gravity is approximately 2 times 10 to the 12th meters per second squared, 2 trillion meters per second squared. That is 200 billion times the gravity on Earth's surface. If you could somehow survive the journey to a neutron star surface and stood on it, and stood is doing a lot of work in that sentence because you would be instantly and catastrophically destroyed, you would weigh, personally, about 15 billion tons. Your weight on Earth is a comfortable 70 or 80 kilograms. On a neutron star, you would weigh 15 billion tons. The escape velocity from a neutron star surface is roughly 100,000 kilometers per second, approximately a third of the speed of light. To escape from a neutron star, you would need to be moving at 100,000 kilometers per second when you launched. For context, the fastest spacecraft ever launched from Earth, NASA's Parker Solar Probe, reached a top speed of about 192 kilometers per second near perihelion. To escape a neutron star, you would need to be moving roughly 520 times faster than that. And these extreme numbers, the density, the gravity, the escape velocity, are not the most extreme properties of the most extreme neutron stars. We will encounter far stranger things before this documentary is done.
Here is something remarkable. Neutron stars were predicted theoretically long before they were ever observed. In 1934, 33 years before Jocelyn Bell's discovery, two astronomers named Walter Bade and Fritz Zwicky published a remarkable paper. Bade was German, trained in Hamburg and Göttingen. Zwicky was Swiss-Bulgarian, famously cantankerous, brilliant, and often underappreciated in his own lifetime. Together, they proposed something extraordinary for the era. They suggested that when a massive star runs out of fuel and its core collapses, the result could be an incredibly dense star composed mostly of neutrons, a neutron star, as they named it. They also proposed that the energy released in this collapse would power a supernova explosion. In the same paper, published just 2 years after James Chadwick discovered the neutron itself, Bade and Zwicky essentially described the modern picture of core collapse supernovae and their neutron star remnants. The astrophysical community, for the most part, was not impressed. The idea seemed too exotic, too extreme. A star the density of an atomic nucleus? Stars the size of cities with the mass of the sun? Many dismissed it as speculation. Zwicky, in particular, was difficult to dismiss and difficult to like. He was famously abrasive. He called his colleagues at Caltech spherical bastards, explaining that they were bastards when looked at from any direction. He was also frequently right when everyone else was wrong. He predicted the existence of dark matter in galaxy clusters in 1933. He cataloged supernovae prolifically. He designed a new type of jet engine during World War II, and he predicted neutron stars completely correctly 33 years before anyone found one. History has vindicated him on all of these, but the vindication, in most cases, came too late for Zwicky to fully savor it. He died in 1974, the same year Hewish received the Nobel Prize for the discovery of pulsars, the objects Zwicky had predicted 40 years earlier. In 1939, J. Robert Oppenheimer, who would later lead the Manhattan Project, and his student George Volkoff published a more rigorous theoretical treatment of neutron stars, building on work by Richard Tolman. The Tolman-Oppenheimer-Volkoff equation, or TOV equation, describes the structure of a neutron star in general relativity and predicts the maximum mass a neutron star can sustain before collapsing into a black hole. Their estimate for this maximum mass was approximately 0.7 solar masses. We now know this was too low. Oppenheimer and Volkoff were using simplified nuclear physics, but the framework they established remains the foundation of neutron star theory today. 30 years passed. The theoretical framework sat, largely untested, in the literature.
Then, a young woman in a Cambridge field found a repeating signal in the noise, and 30 years of theory suddenly had something to test itself against. But here is where the story takes its first deeply unsettling turn. As more pulsars were discovered, as more observations accumulated, as the initial euphoria of confirmation settled into the long work of careful measurement, something began to emerge from the data. The neutron stars we were finding did not always behave the way our equations predicted they should. The masses were different, the sizes were different, the way they spun and glitched and flared and pulsed, it didn't always match. And as we pushed deeper into the data, the discrepancies didn't disappear, they grew. The evidence was telling us something we didn't want to hear, that the physics inside a neutron star was not the physics we thought we knew. But the evidence forces us to confront an uncomfortable possibility. Inside the most extreme objects in the universe, physics as we understand it breaks down. And what lies in that darkness, what actually constitutes the core of a neutron star, remains even today one of the deepest unsolved problems in all of science.
Science advances through the grinding friction between theory and observation. Theory makes a prediction, observation tests it. If the prediction is wrong, the theory changes. This is the basic engine of scientific progress, and nowhere has that engine run harder in the past 2 decades than in the physics of neutron stars. The fundamental theoretical question is this: what is the equation of state of the matter inside a neutron star? The equation of state is, in essence, the rule book for a material. It tells you, given a certain density and temperature, what the pressure will be. Get the equation of state right, and you can calculate the relationship between a neutron star's mass and its radius, predict when it will collapse into a black hole, and determine what exotic phases of matter exist at its core. Get it wrong, and nothing else works. For most of the 20th century, physicists worked with equations of state derived from nuclear physics, the physics of atomic nuclei, tested and validated in laboratories and particle accelerators. These models consistently predicted that neutron stars should have a maximum mass of roughly 1.5 to 2 times the mass of the Sun. Exceed that limit, they said, and the star collapses into a black hole. The upper end of this range is now called the Tolman-Oppenheimer-Volkoff limit, though the original 1939 calculation gave a much lower value. Subsequent nuclear physics refinements pushed the predicted maximum upward toward 2 solar masses, but not much beyond. And then, in 2010, something happened that sent shockwaves through the theoretical physics community. A team led by Scott Ransom and Paul Demarest at the National Radio Astronomy Observatory in the United States was monitoring a pulsar designated PSR J1614-2230. This pulsar has a companion, a white dwarf star, orbiting the pulsar in a binary system with an orbital period of just 8.7 days. The 2 stars are sufficiently close and massive that the effects of general relativity are significant. Space-time itself is measurably curved in their vicinity. This curvature is measurable. When the white dwarf passes between Earth and the pulsar, when it eclipses the pulsar from our line of sight, the radio pulses from the pulsar must travel through the gravitational field of the white dwarf. This slightly delays them. The effect is called the Shapiro delay, predicted by Erwin Shapiro in 1964. The size of the Shapiro delay depends on the masses of both stars. By measuring the delay with extraordinary precision using the Robert C. Byrd Green Bank Telescope in West Virginia, one of the largest fully steerable radio telescopes in the world, Demarest's team could calculate the masses of both objects. The white dwarf mass came out at 0.5 solar masses, unspectacular. The pulsar mass, 1.97 solar masses,
with an uncertainty of just 0.04 solar masses, nearly twice the mass of the Sun, in a sphere, as we will discuss shortly, of roughly 12 kilometers radius. The internal density required to support this mass reaches levels that exceed anything testable in any laboratory on Earth, not by a factor of 2 or 3, by many orders of magnitude. We are in entirely uncharted territory, and the chart, as it turns out, had been drawn wrong.
Mass tells us one dimension of the neutron star equation of state, but mass alone is not enough to nail down the physics. For that, we need the radius too. Think of it this way. If I tell you that a box weighs 5 kilograms, I can't tell you whether it's filled with polystyrene foam or lead. The mass doesn't distinguish between a large, fluffy, soft interior and a small, compact, hard one. I need both the mass and the size to calculate the density, and the density is what constrains the physics. For neutron stars, measuring the radius is extraordinarily difficult. They are small, they are far away, and while they glow in X-rays, extracting a precise size from those X-ray observations requires accounting for enormous numbers of confounding factors. The interstellar gas between us and the star, the properties of its atmosphere, the effects of its intense gravity on the light escaping its surface. The breakthrough came with an instrument called NICER, the Neutron Star Interior Composition Explorer. NICER is a NASA X-ray telescope, but it is not a conventional space observatory. It sits, somewhat incongruously, mounted on a truss of the International Space Station, staring at millisecond pulsars as the ISS orbits Earth at 28,000 kilometers per hour. NICER was launched in June 2017, and its primary scientific mission is beautifully elegant. Millisecond pulsars have hotspots at their magnetic poles, regions where charged particles spiral down into the star's atmosphere and heat it to temperatures well above the average surface temperature. These hotspots glow brightly in X-rays, and as the star rotates, the hotspots sweep in and out of view, creating a characteristic pulse profile, the X-ray equivalent of the radio lighthouse pulse. Here's the key insight. The shape of that pulse profile is not arbitrary. It is sculpted by general relativity. As X-rays leave the neutron star's surface, they travel in an intense gravitational field. This field bends their paths, a phenomenon called gravitational light deflection, predicted by Einstein. The amount of bending depends on the star's compactness, the ratio of its mass to its radius. A compact star, small and massive, bends light more strongly than a less compact one. This bending affects the pulse profile in predictable ways. By measuring the pulse profile with extreme precision and modeling it through general relativistic ray tracing calculations, NICER can infer the star's radius, its mass, and even the geometry of its hotspots. In 2019, NICER published its first results. The target was PSR J0030 plus 0451, a millisecond pulsar approximately 1,000 light-years from Earth. The result, the star has a mass of approximately 1.34 solar masses and a radius of approximately 13.02 kilometers. But there was a surprise. The modeling of the hotspots suggested that they were not located at the magnetic poles in the configuration theorists expected. Instead of two hotspots at opposite poles, the data suggested a more complex geometry, possibly a crescent-shaped hot region and a smaller circular one, both in the same hemisphere. The exact geometry of the neutron star's magnetic field, something that had been assumed to be simple, turned out to be far more complicated than anyone predicted. This matters because it affects our understanding of how the radio beams are generated, how energy flows in the magnetosphere, and ultimately how the star evolves. Even the relatively simple surface and near-surface physics of neutron stars is turning out to be more complex than we assumed. In 2021, NICER published results for the more massive pulsar, PSR J0740 plus 6620, the 2.14 solar mass record holder, using both NICER data and data from ESA's XMM Newton X-ray Observatory. The radius, approximately 12.35 kilometers, with an uncertainty range of roughly 11 to 14 kilometers at the 68% confidence level. Combined with the Demarest ransom mass measurement, this gives us a density at the star's center that is almost inconceivably extreme, and the radius measurement is consistent with what theorists call a moderately stiff equation of state. Neither the softest models, which would predict a smaller star, nor the stiffest, which would predict a larger one. The data is boxing in the answer. Many theoretical possibilities have been eliminated. A region of possibility remains, and within that region, the most compelling models suggest that the core of the most massive neutron stars contains matter in an exotic state, something beyond ordinary neutrons. But this represents just one piece of a much larger puzzle.
We have spoken about pulsars as the most precise natural clocks in the universe, and this is true. Over long timescales, their rotational stability rivals atomic clocks in precision. But precision and perfection are not the same thing, and occasionally, without warning, the clock breaks. Not permanently, just for a moment, but that moment tells us something extraordinary about the interior. The phenomenon is called a pulsar glitch. Without any precursor, without any detectable warning signal, the rotation rate of a pulsar suddenly jumps. The period decreases, the pulsar speeds up by a tiny but measurable amount. Then, over the following days and weeks, it gradually relaxes back toward its pre-glitch spin rate, though it typically doesn't return all the way to the original value. There is usually a permanent, small offset. These glitches have been observed in hundreds of pulsars since the first was detected in the Vela pulsar in 1969, just 2 years after Bell's initial discovery. The Vela pulsar, a relatively young neutron star, about 1,000 light-years away in the constellation Vela, is the most prolific glitcher known. It has glitched more than 20 times in the decades we have been monitoring it, with glitch intervals ranging from several months to a few years. The leading explanation for glitches involves the neutron superfluid interior. Inside a neutron star, below the outer crust, the neutrons are expected to exist in a superfluid state, a quantum mechanical condition in which matter flows with absolutely zero viscosity. This superfluid forms rotating vortices, and these vortices tend to pin themselves to the crystal lattice of the inner crust. When the crust slows down due to magnetic braking, the star radiating away rotational energy as electromagnetic radiation, the superfluid continues spinning faster. The rotational velocity difference between the two builds up. Eventually, something triggers a sudden unpinning of the vortices. The angular momentum of the faster spinning superfluid is abruptly transferred to the crust, which suddenly speeds up. Think of it like this. Imagine a spinning top inside a container of syrup. The top keeps spinning faster than the container. Suddenly, the syrup grabs the container and spins it up. That is a glitch. But in 2021, something happened to the Vela pulsar that this model does not predict. During a glitch event, high-speed radio timing with the Meerkat telescope in South Africa caught something that had never been observed before, a brief transient period during the glitch in which the pulsar momentarily slowed down, sped up slightly from its pre-glitch rate, then slowed, then resumed its acceleration. A glitch with a dip, an anti-glitch embedded within a glitch. This behavior is incompatible with the simple vortex unpinning model. It suggests that the coupling between the superfluid interior and the solid crust is more complex, possibly involving multiple superfluid components in different layers, or a different mechanism entirely, operating at the crust core boundary. The basic thing we can measure about a neutron star's interior, its rotation, is telling us the structure is stranger than we thought. The evidence suggests something far stranger than anyone predicted.
On August 17, 2017, at 12 hours, 41 minutes, and 4 seconds Coordinated Universal Time, the most scientifically productive single astronomical observation in human history began. On that day, 2 neutron stars, dead remnants of stars that had burned and exploded billions of years before, completed a merger that had been centuries in the making in geological terms, and billions of years in the making in astronomical terms. They had been orbiting each other in an ever-tightening spiral, losing energy to gravitational radiation with each orbit, drawing closer and closer across the billions of years since they were born. On August 17, 2017, they finally collided, and we were watching. The Laser Interferometer Gravitational Wave Observatory, LIGO, consists of 2 facilities, one in Livingston, Louisiana, and one in Hanford, Washington. Each facility is an L-shaped vacuum chamber with arms 4 kilometers long. A laser beam is split and sent down each arm, reflected off suspended mirrors and recombined. If a gravitational wave passes through, a ripple in space-time itself, it stretches one arm and squeezes the other by an almost unimaginably small amount. The measurement LIGO makes is a change in arm length of approximately 1/1000th the diameter of a proton. To achieve this, LIGO has to isolate itself from every conceivable source of noise. The mirrors are suspended on multi-stage pendulums to isolate them from seismic vibration. The laser systems are engineered to levels of stability that were considered impossible 20 years ago. The entire facility is enclosed in the most perfect vacuum achievable in a large-scale engineering project. Even the quantum noise of the photons in the laser beam, the Heisenberg uncertainty principle, has to be accounted for and mitigated. On the morning of August 17th, LIGO, along with its European partner Virgo, which had just come online days earlier, detected a signal designated GW170817. Unlike the previous black hole merger signals, which were brief chirps lasting a fraction of a second, GW170817 lasted 100 seconds. It was a rising spiral in frequency, a chirp that climbed from about 24 Hz at the beginning of the signal to over 1,000 Hz at merger, representing the last 100 seconds of an orbital inspiral that had lasted, before that, for billions of years. It was the gravitational wave equivalent of hearing the last notes of a symphony that had been playing since before the Earth existed. 1.7 seconds after the gravitational wave signal terminated, 1.7 seconds after the merger itself, NASA's Fermi Space Telescope registered a burst of gamma rays from the same direction in the sky. This confirmed, definitively and for the first time, something that had been suspected but never proven, that short gamma ray bursts, mysterious flashes of high-energy radiation that had puzzled astronomers since the 1960s, are caused by neutron star mergers. In those 1.7 seconds between merger and gamma ray burst, something had happened. A jet of material was launched, punched through the debris cloud, and produced the burst. The physics of exactly how this happens is still being worked out. Then, and this is where August 17, 2017 becomes truly extraordinary, the alerts went out. Every major telescope on Earth and in space was notified.
Astronomers around the world dropped what they were doing and swung their instruments toward the source galaxy, NGC 4993, a lenticular galaxy in the constellation Hydra, 130 million light-years away. What they found, glowing in the aftermath of the merger, was a kilonova, a transient light source powered by the radioactive decay of newly synthesized heavy elements ejected by the collision. Over the following days and weeks, 70 different telescopes observed the kilonova in wavelengths from gamma rays to radio waves. The spectroscopic data, the chemical fingerprints in the light, told an unmistakable story. Strontium was there, barium was there, gold was there, platinum, uranium, iodine, cesium, element after element, forged in the heat and neutron flux of the collision and flung into intergalactic space. The gold in your jewelry, the gold in every vault, every circuit board, every piece of jewelry, every Olympic medal ever awarded in the history of human civilization, it was not made in a living star. It was not assembled slowly over millions of years. It was made in an event like this: two dead stars colliding in a fraction of a second of incomprehensible violence, scattering their newly forged atoms across the cosmos. We watched the universe make gold in real time, 130 million light-years away. But for neutron star physics specifically, the most important thing about GW 170817 was not the gold, it was the shape of the gravitational wave signal. In the final moments of the inspiral, in the last few milliseconds before merger, the gravitational wave signal carries information about how the neutron stars were distorted by each other's tidal fields. As the stars got close, their mutual gravity began to stretch each star into an ellipsoid, like squeezing a stress ball. The amount of stretching depends on how compressible the star is, in other words, on the equation of state. A soft equation of state produces a star that deforms easily. It's compressible, like water. A stiff equation of state produces a star that resists deformation, like a hard rubber ball. The signal from a soft equation of state merger looks subtly different from a stiff equation of state merger. This quantity, called the tidal deformability, was extracted from GW 170817 with surprising precision. The result, the neutron stars were not very deformable. The equation of state is moderately stiff. The stars were probably between 11 and 14 kilometers in radius, consistent with and now combined with the nicer measurements to close in on the truth. GW 170817 was, in short, a simultaneous measurement of neutron star mass, radius, tidal deformability, and equation of state constraints, all from a single 100-second GW wave signal and its electromagnetic aftermath. Nothing has contributed more to our understanding of dense matter in a single event. The evidence extends beyond individual pulsars into the realm of multi-messenger astronomy, a new era of cosmic understanding that GW 170817 inaugurated.
We have described neutron stars as extreme. The density, the gravity, the spin, all the most extreme values of any known material object in the universe. But within the neutron star family, there is a subclass so extreme that it makes ordinary pulsars look positively mild. They are the most magnetically powerful objects ever observed in nature. They produce the brightest explosions in the galaxy. They can ionize Earth's atmosphere from across half the Milky Way. They are called magnetars. A typical pulsar has a magnetic field roughly 1 trillion times stronger than Earth's, approximately 10 to the 12 Gauss, compared to Earth's 0.5 Gauss. This is already extraordinarily powerful. It is strong enough to fundamentally alter the structure of atoms in the neutron star's atmosphere, stretching them into cylinders along field lines. A magnetar exceeds even this by a factor of 1,000 or more. Magnetar field strengths reach 10 to the 14 to 10 to the 15 Gauss. Let me give you a sense of what that means in practical terms. At a distance of roughly 1,000 kilometers from a magnetar, about the distance from London to Berlin, the magnetic field would be strong enough to distort the electron clouds of atoms in your body, fundamentally altering your chemistry at the atomic level. At a distance of roughly 160,000 kilometers, less than half the distance to the moon, the magnetic field would strip the iron from your hemoglobin molecules, pulling it through your skin. Your blood would be destroyed at the atomic level by pure magnetism before any other effect killed you. At the distance of the moon from Earth, a magnetar would be fatally dangerous. There are approximately 30 known magnetars in our galaxy. Given the difficulty of detecting them, they are quiescent for most of their existence. The true number is likely much higher. On December 27, 2004, one of these objects performed the most violent act ever observed from an astrophysical source within our galaxy. The culprit was SGR 180620, a magnetar located approximately 50,000 light-years away on the far side of the Milky Way in the constellation Sagittarius. SGR stands for Soft Gamma Ray Repeater, a class of objects known for occasionally producing bursts of gamma-ray and X-ray energy. SGR 180620 had been monitored since the 1990s. It was known to flare occasionally. Nothing prepared observers for what happened that December morning. In 0.2 seconds, 1/5 of a single second, SGR 180620 released more energy than our Sun radiates in 250,000 years. The burst was so powerful that it measurably ionized Earth's upper atmosphere, the ionosphere, from a distance of 50,000 light-years. This caused a temporary increase in the ionosphere electron density, comparable to what happens during a powerful solar flare, but from an object on the other side of the galaxy. Multiple spacecraft instruments were overwhelmed and temporarily blinded by the burst. The RHSSI satellite, the Integral Telescope, and others were saturated. The signal was simply too strong for their detectors to handle. Had SGR 180620 been located 10 light-years from Earth, just over 2 light-years closer than Alpha Centauri, that single half-second burst would have been energetically comparable to the event that triggered Earth's Ordovician mass extinction 443 million years ago, which is itself linked by some researchers to a nearby gamma-ray burst. The magnetar flare would have been an extinction event. It was 50,000 light-years away, and it still altered our atmosphere. How does a magnetar produce such power? The leading theoretical model, developed in the early 1990s by Robert Duncan at the University of Texas and Christopher Thompson at the University of Toronto, invokes a process that occurs in the first seconds of the neutron star's life. When a neutron star is born, if it is rotating rapidly enough, the intense convection occurring in the hot interior can act as a dynamo, the same physical mechanism that generates Earth's and Sun's magnetic fields, but operating under conditions of incomprehensible violence. If the convective cells turn over fast enough, they can amplify the magnetic field exponentially during the first 10 to 30 seconds of the star's existence. The result is a neutron star with a field 1,000 times stronger than a normal pulsar, a magnetar. The field carries an enormous amount of energy, up to 10 to the 46th joules for the strongest magnetars. And this field is not static. It evolves, it moves, it stresses the solid crust of the neutron star. Occasionally, when the magnetic stress becomes too great, the crust cracks, a magnetar starquake. The sudden motion releases energy as X-rays and gamma rays.
In the most extreme cases, called giant flares, the crust ruptures extensively and the magnetic field erupts outward in a catastrophic rearrangement. This is what happened on December 27, 2004. And this brings us at last to one of the most mysterious astrophysical phenomena of the past 2 decades, a phenomenon that connects magnetars to signals arriving from billions of light-years away, signals so bright we can detect them from the edge of the observable universe, signals whose origin puzzled astronomers for a decade: fast radio bursts. And that story begins in an archive of old telescope data reviewed by a graduate student in 2007 who found a signal that shouldn't have been there.
In 2007, Duncan Lorimer, a radio astronomer at West Virginia University, and his student David Narkovich were doing something that sounds familiar by now: reviewing archival data. Old observations taken by the Parkes Radio Telescope in Australia in 2001, sitting in storage on magnetic tape, unanalyzed. Lorimer and Narkovich were searching for new pulsars in the data. They found something else entirely: a single radio pulse lasting approximately 5 milliseconds, extraordinarily bright, one of the brightest radio signals ever received from outside the solar system, and critically, showing a dispersion measure, the signature of having traveled through ionized plasma that corresponded to a source not within our galaxy, but billions of light-years away, extragalactic. This was unprecedented. No known natural phenomenon produced bright, extragalactic radio pulses like this. Lorimer published the finding in 2007, somewhat tentatively, suggesting it might be a new class of astrophysical transient, but acknowledging that with only a single example, it was impossible to be certain. For several years, the scientific community was cautious. Some argued the signal might be terrestrial interference. Some proposed exotic explanations involving cosmic strings or evaporating black holes. The single example, dubbed the Lorimer burst, sat unconfirmed for years. Then, in 2013, a team at Parkes discovered 4 more. Then others began turning up in other telescope archives. By 2020, the count was in the hundreds. By 2023, the CHIME telescope in Canada alone had published a catalog of over 500 fast radio bursts, the largest ever assembled. The phenomenon was real, it was common, and it was completely mysterious. Each burst lasts only milliseconds. Each arrives from a fixed celestial direction. Each shows dispersion consistent with having crossed billions of light-years of intergalactic space. Some repeat. The same position in the sky produces multiple bursts, days, weeks, or months apart. Most, as far as we can tell, do not. The energy required to produce a detectable signal from billions of light-years away is staggering. In its millisecond of activity, a typical fast radio burst releases energy in radio waves equivalent to what our sun emits in radio waves over several days, or, depending on the burst, over weeks or even months, from a source the size of a city or smaller in a millisecond. Magnetars immediately emerged as a leading candidate source. The timescale was right. Millisecond durations suggest a compact object, and neutron star magnetospheres are known to produce brief, intense radio emission. The energy was plausible. The lack of repetition for most bursts was explainable if each burst depletes magnetic energy that requires time to rebuild. But the connection was theoretical until April 28, 2020. On that date, the Canadian Hydrogen Intensity Mapping Experiment, CHIME, and the Survey for Transient Astronomical Radio Emission, 2, STARE-2, both detected a fast radio burst, not from a billion light-years away, from within the Milky Way. From SGR 1935-2154, a magnetar in our own galaxy, approximately 30,000 light-years away. For the first time, a fast radio burst had a confirmed source, and it was a magnetar.
This was an enormously significant confirmation. The burst from SGR 1935-2154 was detectable with ground-based radio telescopes, something that had never been possible for extragalactic FRBs, which required sensitive space-based or dedicated ground-based instruments. It meant that the mechanism producing fast radio bursts could now, in principle, be studied in detail using the full arsenal of astronomical tools. But there is a catch. The burst from SGR 1935-2154 was, compared to typical extragalactic FRBs, approximately 1,000 times less luminous. To explain the brightest extragalactic bursts with a magnetar model, either those magnetars must be extraordinarily more powerful than anything in our galaxy, or the mechanism must be much more efficient than what we observed with SGR 1935-2154. Some researchers suggest that the most luminous FRBs come from newly formed magnetars, objects just seconds or minutes old, when their magnetic fields are freshest and most energetic. Others invoke geometric effects, such as coherent emission from multiple regions of the magnetosphere, combining constructively. Still others propose a completely different mechanism, not magnetic reconnection at the stellar surface, but a shock wave in the outflow of material at large distances from the star. The repeating FRBs add another layer of complexity. FRB 201201102, the first confirmed repeater, was localized to a dwarf galaxy at cosmological distance and found to reside within a dense, magnetized nebula, consistent with a young magnetar surrounded by the remnant of its birth supernova. But it repeats hundreds of times, with no clear sign of slowing down. A magnetar draining its magnetic energy through FRBs should, over time, become less active. FRB 201201102 shows no such decline. There's a periodicity puzzle, too. Several FRBs show activity cycles, periods of bursting alternating with periods of silence, on timescales of days to months. One, FRB 202201124, showed particularly complex behavior, bursting furiously for days, then going silent for weeks, then bursting again. During its active periods, the burst characteristics changed from burst to burst in ways suggesting a dynamic, evolving magnetosphere. This is not the behavior of a simple, stable, rotating neutron star. This is the behavior of something complex, turbulent, and in a state of ongoing change. The honest answer is that we do not fully understand fast radio bursts. We have a confirmed galactic source. We have strong circumstantial evidence pointing to magnetars as the primary engine. We have a rich observational data set of hundreds of bursts with varied properties, and we have a collection of theoretical models that each explain some of the data, but none of the data fully. What we know for certain is this: somewhere in the universe, possibly every second, a neutron star is producing a burst of radio energy that briefly outshines entire galaxies of hundreds of billions of stars in the radio spectrum, and we are only just beginning to understand why.
Let us now step back from the individual phenomena and ask the overarching theoretical question that all of this evidence is trying to answer. What is the equation of state of dense nuclear matter? This question sounds technical. It is, in practice, one of the deepest questions in all of physics. It asks, what are the fundamental rules governing matter when it is compressed beyond the limits of anything we can test in a laboratory? What happens to the strong nuclear force, the force that holds atomic nuclei together, when matter is squeezed to densities many times greater than the densest atomic nucleus? The theory of the strong nuclear force is called quantum chromodynamics, or QCD. Developed in the 1970s, QCD describes how quarks, the fundamental constituents of protons and neutrons, interact via the exchange of particles called gluons. QCD is extraordinarily well tested at high energies.
Experiments at CERN and Fermilab have confirmed its predictions with tremendous precision. But QCD has a problem. At low energies and high densities, precisely the conditions in a neutron star core, QCD becomes extremely difficult to calculate. The mathematics become what physicists call non-perturbative. You can't solve it by the usual method of expanding in small corrections. The equations describe a system where the interaction is so strong that every particle is significantly affecting every other particle simultaneously. This is why the neutron star equation of state is unknown, not because we lack a theory. We have the theory, QCD. We just can't solve it for the conditions we care about. Theorists use several approaches to circumvent this. At low densities, up to about twice nuclear saturation density, which is the density of an atomic nucleus, we can use nuclear physics models calibrated on laboratory experiments with heavy nuclei. These models are constrained by measurements in laboratories like those at Riken in Japan, CERN's Isolde facility, and the Facility for Rare Isotope Beams at Michigan State University in the United States. They give confident predictions for the behavior of matter at the outer layers and intermediate interior of a neutron star. The problem is the middle, between roughly 2 and 8 times nuclear saturation density, precisely where the transition between ordinary nuclear matter and any exotic phase would occur. Neither the nuclear physics models nor the perturbative QCD calculations are reliable. This is a no-man's land in the theoretical landscape, and it is precisely the region most relevant to understanding what is at the core of a 2-solar mass neutron star. Into this gap, theorists have proposed various exotic phases. Hyperonic matter. At sufficiently high densities, it becomes energetically favorable for neutrons to transform into heavier baryons called hyperions, particles containing strange quarks. Lambda hyperions, sigma hyperions, xi hyperions. These are unstable in ordinary conditions, but inside a neutron star, the enormous Fermi energy of the neutrons makes their conversion into hyperions thermodynamically advantageous. The problem, known as the Hyperion puzzle, is that most models, including hyperions, predict a maximum neutron star mass well below 2 solar masses. The observed 2 solar mass stars seem to rule out much of the Hyperion parameter space. Quark matter. At even higher densities, quarks become deconfined. The strong force can no longer keep individual quarks locked inside protons and neutrons, and they form a free soup of quarks and gluons. This is quark-gluon plasma, the state of matter that filled the universe in its first microsecond. In neutron star cores, this matter would be cold, dense quark-gluon plasma, different from the hot, dilute plasma created at particle colliders. Models suggest this matter might be in a state called color superconductivity, where quark pairs form a condensate analogous to the Cooper pairs in a superconductor, but governed by the color charge of QCD rather than electric charge. Strange quark matter. Edward Witten proposed in 1984 that the ground state of matter, the most stable configuration possible, might not be ordinary iron, but a 3-flavor quark soup, roughly equal parts up, down, and strange quarks. If this Witten conjecture is correct, then inside neutron stars, the nucleons might spontaneously dissolve into stable strange quark matter. Objects made entirely of strange quark matter, from surface to core, are called strange quark stars, or strangelets. They would be slightly smaller and denser than neutron stars of the same mass, and would cool at a different rate. A team from the University of Helsinki and CERN, in a 2020 paper in Nature Physics, led by Tyler Gorda, Alexei Korkela, and Alexei Voronin, performed a Bayesian analysis combining all available observational constraints with their perturbative QCD calculations. Their conclusion:
In neutron stars above 2 solar masses, the probability of a quark core exceeds 80%. This forces us to reconsider fundamental assumptions about matter itself. We may be observing in these distant dead stars the only surviving relic of a state of matter that last existed freely in the entire universe when the universe was 1 microsecond old.
Science does not stand still. Every mystery we have described in the past 2 hours is the target of ongoing research using instruments either already operating, under construction, or in detailed planning. The next decade promises a cascade of discoveries that will, piece by piece, close in on the equation of state of dense matter. Let us tour the frontier. LIGO's ongoing evolution. The gravitational wave detectors at LIGO have been upgraded multiple times since their first detection in 2015. The current configuration, Advanced LIGO Plus, has sensitivity improvements that extend the detectable volume by roughly a factor of 3 compared to the instrument that detected GW170817. In the fourth observing run, which began in 2023, the network, including Virgo in Italy and Kagra in Japan, detected multiple candidate neutron star merger events. Full analysis of these detections, incorporating the tidal deformability measurements, will add statistically to the constraints on the equation of state. In the physics of neutron star interiors, more events means more precise answers. Beyond LIGO A+ lies the Einstein telescope, a proposed third-generation European gravitational wave observatory planned for construction in either the Netherlands-Belgium region or in Sardinia, Italy. The Einstein telescope would be an equilateral triangle of underground tunnels, each arm 10 kilometers long, compared to LIGO's 4 kilometers. Underground location dramatically reduces seismic noise at low frequencies. The result would be a detector roughly 100 times more sensitive than the original advanced LIGO, capable of detecting neutron star mergers not just to 130 million light-years, like GW170817, but across virtually the entire observable universe. At those detection rates, potentially hundreds of events per year, the statistical analysis of tidal deformabilities would constrain the equation of state to a level of precision that would definitively rule in or rule out quark matter cores in neutron stars. The uncertainty that currently clouds the question would dissolve into a clear answer. NICER's continued operation and the future of X-ray timing. NICER continues to operate on the ISS and is accumulating data on additional millisecond pulsars. Each additional mass-radius measurement narrows the allowed equation of state parameter space. The planned next-generation mission, STROBE-X, the spectroscopic time-resolving observatory for broadband energy X-rays, would build on NICER's success with a detector area roughly 30 times larger, enabling radius measurements to 5% precision for dozens of neutron stars. Mass radius measurements at this precision would discriminate between competing theoretical models with high confidence. The Square Kilometer Array. The SKA, currently under construction in South Africa and Australia, with first science observations expected in the mid-2020s and full operations in the 2030s, will be the largest radio telescope ever built. With an effective collecting area of 1 square kilometer, it will detect pulsars at sensitivity levels far beyond any current instrument. Estimates suggest the SKA will discover tens of thousands of new pulsars, potentially including pulsars in relativistic binary systems ideal for mass measurements, and millisecond pulsars with timing stability suitable for equation of state constraints. The SKA will also dramatically expand the pulsar timing array datasets, improving the sensitivity of the gravitational wave background. pulsar timing arrays, and the gravitational wave background. In 2023, 4 independent international collaborations, Nanograv in North America, the European Pulsar Array, the Parkes Pulsar Array in Australia, and the Chinese Pulsar Array, simultaneously announced evidence for a stochastic gravitational wave background. This is a sea of overlapping gravitational waves from supermassive black hole binaries across the observable universe. With continued monitoring over the next decade, this background will be measured with sufficient precision to probe the population statistics of neutron stars and black holes across cosmic time. Neutrino detectors watching for the next galactic supernova. The last nearby supernova was SN 1987L in the Large Magellanic Cloud, 167,000 light-years away. The next galactic supernova could occur at any time, and when it does, it will produce a neutrino burst detectable to current and future underground detectors. The IceCube Neutrino Observatory at the South Pole, the Super Kamiokande detector in Japan, and the forthcoming Hyper Kamiokande and Juno detectors would each record thousands of neutrino events from a galactic core collapse. The time profile of these neutrinos encodes information about the proto-neutron star's equation of state in its first few seconds of existence, conditions even more extreme than the cold, old neutron stars we usually observe. Recent breakthroughs suggest the pace of discovery is accelerating. Between LIGO's detections, NICER's measurements, the pulsar timing array results, and the magnetar connection to fast radio bursts, the past 5 years have produced more constraints on dense matter physics than the previous 30. The curve is steep. The answers are approaching.
We have spent a great deal of time in this story talking about extreme physics, about masses and radii and equations of state and gravitational wave signals. It would be easy, in the midst of all that technical detail, to lose sight of why any of this matters, not scientifically, but personally. What does it mean to you, watching this, that neutron stars exist, that they are what they are? The answer, it turns out, is more direct and more personal than you might expect. Begin with the most literal connection, the elements in your body. Every atom of every element heavier than iron in your body, every atom of iodine in your thyroid. We have spent a great deal of time in this story talking about extreme physics, about masses and radii and equations of state and gravitational wave signals. It would be easy, in the midst of all that technical detail, to lose sight of why any of this matters, not scientifically, but personally. What does it mean to you, watching this, that neutron stars exist, that they are what they are? The answer, it turns out, is more direct and more personal than you might expect. Begin with the most literal connection, the elements in your body. Every atom of every element heavier than iron in your body, every atom of iodine in your thyroid gland, every atom of selenium in your enzymes, every atom of zinc and copper and cobalt and nickel was made, at least in part, in neutron star mergers. The R process, rapid neutron capture, requires an environment flooded with free neutrons, where nuclei can absorb neutrons faster than they decay. Neutron star mergers provide this environment. In the seconds after 2 neutron stars collide, the ejected material is so dense in neutrons that heavy nuclei are assembled from seed nuclei at an extraordinary rate. The strontium detected in GW170817's kilonova is the same strontium used in fireworks to produce brilliant reds. It was made in a neutron star merger and scattered across the cosmos, some of it eventually finding its way into gas clouds that formed new solar systems, new planets, new oceans and atmospheres, and eventually living things. We are, in the most precise and literal sense, made partly of the debris of neutron star collisions.
The heavy elements in our bodies were forged in events like GW 170817, long before the Sun existed, and incorporated into our solar system's formation 4.6 billion years ago. But the connection goes deeper than chemistry. Neutron stars are one of the places where the universe tests the limits of its own laws. Physics, as we know it, has rules that hold everywhere we have ever tested them, from the subatomic to the cosmological. But in the cores of massive neutron stars, those rules encounter conditions so extreme that we genuinely don't know if they still apply in the forms we have written them down in. The equation of state problem is, at bottom, a question about whether our understanding of the fundamental forces of nature, the forces that hold matter together, is complete. It probably isn't. The history of physics is a history of assumptions held confidently until they weren't. Newtonian gravity was complete until Mercury's orbit revealed its limits. Classical physics was complete until the photoelectric effect and atomic spectra revealed quantum mechanics. Special relativity was complete until gravity required general relativity. In each case, the old theory didn't disappear. It remained valid in its domain of application, but the universe revealed that the domain had edges. Neutron stars are edges. They are the places where our currently valid theories run up against their limits, where the next deeper theory of matter, whatever QCD evolves into at high densities, or whatever unified framework replaces our current picture of the fundamental forces, must reveal itself. Every measurement we make of a neutron star's mass, its radius, its tidal deformability, its cooling rate, its glitch behavior, is a probe of those edges. We are not just studying dead stars, we are studying the boundaries of what is knowable with current physics and pressing against them to find out what lies beyond. And there is something else, something more personal still. When Jocelyn Bell sat in that Cambridge field in 1967 and noticed a small, regular blip in the noise, she was a graduate student doing what graduate students do: patient, careful, unglamorous work. She had no idea what she had found. She called it scruff. She flagged it in the margin and moved on. That moment, that flagging of scruff in a margin is, in retrospect, one of the most significant moments in the history of astrophysics. Not because Bell was a genius who immediately saw the importance of what she'd found. She didn't, not immediately, but because she was doing what good science requires above all else, paying close attention. The universe does not announce its secrets with fanfare. It hides them in noise, in the margins of data, in the small, irregular signals that are easy to dismiss as interference. The history of neutron star science, from Bell's discovery to GW 170817 to the 2023 gravitational wave background, is a history of patient attention paid to signals that almost weren't noticed. The universe is patient. It has been producing these signals for billions of years, and it will continue to do so long after we are gone. The question is whether we are paying close enough attention to hear them. We have now arrived at the deepest question, not about pulsars, not about magnetars, not about fast radio bursts or gravitational waves or gold synthesis. Those are extraordinary topics, and we have done them some justice. But they are all, ultimately, observable phenomena, things that happen at the surface of neutron stars, in their magnetospheres, in the collisions and mergers that mark their deaths. The deepest question is about what lies at the center. We cannot see it, not directly. No telescope can peer inside a neutron star. No instrument can resolve the core directly. Everything we know about it is inferred, from mass measurements, from radius measurements, from gravitational wave signals, from cooling rates, from the theoretical constraints of QCD. We are like geologists who study the composition of the Earth's core, not by drilling to it, that is impossible, but by interpreting the seismic waves that pass through it. We are reading the interior of neutron stars in their shadows. And what those shadows suggest is this. At the center of the most massive neutron stars, there is matter that has never been seen freely anywhere in the observable universe since it appeared, briefly, in the first microsecond after the Big Bang. In the first microsecond of the universe's existence, the temperature was so extraordinarily high, trillions of degrees, that matter as we know it did not exist. There were no protons, there were no neutrons. The fundamental particles, quarks and gluons, existed freely, not confined inside hadrons, simply bouncing around in a hot, dense plasma. This is quark-gluon plasma, the primordial state of matter. As the universe cooled, the quarks became confined. The strong force reached out and bundled them into protons and neutrons. From that moment, a microsecond after the Big Bang, free quarks have never been observed in nature, with one exception. The Large Hadron Collider at CERN can briefly recreate quark-gluon plasma by smashing heavy nuclei together at near light speed. The collision is so violent that the quarks are temporarily liberated, but the plasma lasts for a tiny fraction of a second, perhaps 10 to the minus 23rd seconds, before it cools and the quarks reconfine. It is the most transient thing ever created in a laboratory. But in the core of a massive neutron star, if the models are correct, quark-gluon plasma exists permanently, not hot and dilute as in the Big Bang or the LHC, but cold and extraordinarily dense. The quarks are still deconfined. The density is too high for confinement to reassert itself, but they are cold, governed by Pauli exclusion rather than thermal energy. This cold, dense quark matter may be in a state that has no parallel anywhere else in nature. In the strange environment of a neutron star core, QCD predicts that quarks should form Cooper pairs, not of electrons, as in ordinary superconductors, but of quarks. Paired quarks can form a condensate that flows without electrical resistance. This is called color superconductivity, named for the color charge of quarks in QCD. The color superconducting phase of quark matter comes in multiple possible flavors, depending on which quarks pair with which and in what pattern. The phase that theorists believe is most likely at the highest densities is called color flavor locking, where up, down, and strange quarks all pair together in a pattern that simultaneously breaks both color and flavor symmetry. This phase has remarkable properties. It is a perfect conductor of both color and electric charge, and it is also a superfluid. We cannot directly test whether these exotic phases exist inside neutron stars, but their existence or absence would leave signatures. A neutron star with a color superconducting quark core would cool differently from one without. It would have a different moment of inertia and therefore a different glitch behavior. Its tidal deformability would be slightly different. Its gravitational wave signal of its merger would carry a faint imprint. All of these are in principle measurable, not yet with current instruments, but within the capabilities of the next generation of observatories. The most profound implications emerge when we consider what it means that this question, what is matter at the highest densities, may be answerable not in a particle accelerator, but by looking at the sky with better telescopes. The universe has, in effect, built laboratories for us, not the clean, controlled laboratories of human engineering, but natural laboratories operating under conditions we could never engineer, running continuously at densities and pressures billions of times beyond our capabilities, 35 light-years away or 30,000 light-years away. Every neutron star in the galaxy is an experiment we didn't set up, running physics we can't fully replicate, producing data we are only just beginning to read.
There is a boundary in mass beyond which a neutron star cannot exist. Push too much material into a neutron star, and not even the strong force, not even exotic quark matter can resist the relentless compression of gravity. the star collapses further, past the neutron star state, past any state we can describe, and becomes a black hole. This maximum mass, the TOV limit, is one of the most important numbers in astrophysics, and we do not know it precisely. We know it is at least 2.08 solar masses because PSR J0740 plus 6620 is sitting there, stable, mocking our uncertainty. It may be 2.5 solar masses. Some theoretical models allow for maximum masses as high as 3 solar masses, though these require very stiff equations of state that are becoming increasingly constrained by observations. The true value lies somewhere in this range, and its precise location tells us something fundamental about the strong force at its highest densities. This matters for a very practical reason. We need to be able to distinguish neutron stars from black holes. When gravitational wave detectors observe a merger, the masses of the merging objects tell us whether we are looking at 2 black holes, 2 neutron stars, or a mixed pair. But there is a mass gap, a range roughly between 2.5 and 5 solar masses, where objects are rarely observed. Are objects in this mass gap very massive neutron stars or very light black holes? In 2020, LIGO detected GW190814, a merger between a 23 solar mass black hole and an object of 2.6 solar masses. The lighter object sits squarely in the mass gap. Was it the most massive neutron star ever observed, or the lightest black hole? The gravitational wave signal did not show the tidal deformation signature we would expect from a neutron star, consistent with a black hole, but the mass is within the range where some models allow for a very stiff neutron star. No firm conclusion has been reached. The mass gap is a mystery. Resolving it requires both better measurements of the TOV limit and a deeper theoretical understanding of the neutron star equation of state. And there is a deeper puzzle lurking here, the post-merger signal. When 2 neutron stars merge, they don't necessarily immediately form a black hole. If the combined mass is below the TOV limit, the product is a supermassive or hypermassive neutron star, an object that oscillates and radiates gravitational waves at high frequency before eventually collapsing to a black hole through differential rotation dissipation and magnetic braking. The frequency of these post-merger oscillations depends sensitively on the equation of state. If LIGO could detect the post-merger signal, it would provide direct information about the equation of state at densities even higher than those constrained by the pre-merger inspiral. But the post-merger signal is at frequencies of 2 to 4 kHz, higher than LIGO's current peak sensitivity. Next-generation detectors are specifically designed to improve sensitivity in this frequency band for exactly this reason. GW170817 produced no detectable post-merger signal. The merger remnant probably collapsed to a black hole within milliseconds, too quickly to produce a strong oscillation. But future events involving lower-mass neutron stars that might survive as hypermassive neutron stars for longer could reveal this signal. The equation of state is encoded in the post-merger frequency. We simply need the instruments sensitive enough to read it.
Every physical object in the universe has a lifespan. Stars burn and die. Galaxies evolve and transform. Even the universe itself, in the conventional cosmological picture, is not static. It is expanding, cooling, aging. What happens to neutron stars at the end of time? In the near-term astronomical sense, over the next few billion years, neutron stars in binary systems will merge. Some of these mergers will produce black holes. Others, if the combined mass is below the TOV limit, will produce a more massive neutron star. Each merger event produces a kilonova, synthesizing more heavy elements and distributing them into the interstellar medium to be incorporated into future stars and planets.
Isolated neutron stars, those not in binary systems, will spin down. Their rotation slows as they radiate magnetic dipole radiation. Their pulsed radio emission, which depends on both spin rate and magnetic field strength, will gradually cease as they cross the death line, a threshold in period magnetic field space beyond which the radio emission mechanism can no longer operate. They become radio quiet, cooling slowly from millions to hundreds of thousands of degrees over millions of years. On timescales of 1 billion years, a neutron star's surface cools to temperatures below 10,000 Kelvin, too cold to glow in X-rays, too faint to detect invisible light with any current instrument. The star becomes a dark, cold sphere of exotic matter, drifting silently through the galaxy. There may be 1 billion or more such objects in the Milky Way right now, invisible, undetected, drifting through the galactic disk, occasionally passing near other stars, never interacting significantly, carrying within them the frozen record of physics that cannot be unlocked except by another merger. On timescales of 10s to the 34 years, if the proton is unstable, as some grand unified theories predict, with a lifetime around this scale, even the matter in neutron stars will slowly decay. Neutrons, confined within the star, will undergo beta decay into protons, and the protons will subsequently decay into lighter particles. The neutron star will dissolve over unimaginable timescales into a remnant of electrons, positrons, and radiation. If the proton is stable, as experiments at Super Kamikonde and elsewhere currently suggest, setting lower limits on the proton lifetime well above current grand unified theory predictions, neutron stars may persist essentially indefinitely, modulated only by quantum tunneling processes so slow that they take place over timescales of 10 to the 64 years or more. Either way, the final cosmological epoch will be an extremely cold, extremely dark universe in which the most interesting remaining objects are black holes, slowly evaporating through Hawking radiation over timescales of 10 to the 66 to 10 to 100 years. And in the long silence before even that final evaporation, in the dark, cold, nearly featureless universe of the far future, somewhere, two cold, dead neutron stars will find each other, drawn together by gravity across a dark, star-free intergalactic void, spiraling together in a final billion-year approach, and then in a flash of light and gravity and heavy elements cast into an empty cosmos, they will merge. The universe will still be making gold. Long after the last star has burned, long after the last light has faded, the most violent objects in the universe will still be finding each other in the dark. That, perhaps more than anything else in this story, captures what neutron stars are: relentless, extreme, impossible by any ordinary measure of what matter should be able to do, and real, every single one of them, real.
We began with an object smaller than London, heavier than the sun. 3 hours ago, those words were a provocation, a challenge to your intuition about what matter can be. Now, I hope, they are something more, the beginning of an understanding of what the universe actually does with matter when it has no choice but to make it extreme. We have followed the evidence from a Cambridge field in 1967 to the LIGO control rooms in 2017, from the death of massive stars to the birth of gold, from the regular tick of the world's most precise clocks to the catastrophic eruption of the most magnetically powerful objects ever observed, from the surface of a glowing neutron star to the dark, unknown interior that no instrument can yet illuminate. What have we learned? We have learned that neutron stars are not just extreme, they are the universe's way of testing whether its own laws are complete.
Every measurement of a neutron star's mass and radius is a probe of the strong nuclear force under conditions that no laboratory on Earth can replicate. Every glitch in a pulsar's perfect rhythm is a message from the quantum superfluid interior. Every gravitational wave chirp from a neutron star merger is the universe announcing that gold is being made, that heavy elements are being scattered into the cosmos, that matter is being tested against its own limits. We have learned that our equations are incomplete. The equation of state of dense nuclear matter, the fundamental rulebook for what happens to matter above nuclear density, is not yet fully written. Whether exotic quark matter exists at neutron star cores, whether strange quark stars walk among us, whether the maximum mass is 2.1 or 2.5 solar masses, these are open questions, important questions, questions that the next generation of observatories is designed to answer. We have learned that neutron stars are not merely objects of academic interest. They are the forges of the elements that make complex chemistry and complex life possible. The iodine in your body was made in an event like GW170817. The gold in your rings was scattered across a galaxy in a kilonova. You carry, in your chemistry, the record of neutron star collisions that occurred before your solar system formed. We are connected to these impossible objects, not as distant spectators, but as downstream beneficiaries. The violence that created them, the stellar collapse, the supernova explosion, the merger, was the violence that made us possible. And we have learned something about science itself. Jocelyn Bell found her signal not because she was told to look for it, not because any theory predicted it in the form she found it, but because she was paying close attention to data that other people might have dismissed. The scruff in the margin that changed astrophysics forever. The history of neutron star science is more than almost any other field, a history of surprises. Pulsars were unexpected. The glitch phenomenon was unexpected. The mass gap was unexpected. The 1.97 solar mass measurement was unexpected. GW170817 was long awaited but still surprising in its details. The gamma ray delay, the strontium detection, the complex kilonova spectra. The 2023 gravitational wave background was expected theoretically, but still produced gasps of delight when confirmed. The universe, in short, has not been cooperating with our predictions. It has been doing something stranger, more interesting, and more instructive than what we anticipated. And there is every reason to believe that this will continue. Somewhere out in that sky, a pulsar is spinning right now. A magnetar is building toward its next flare. Two neutron stars are orbiting each other, losing energy to gravitational waves, drawing fractionally closer with each revolution. Somewhere, a supernova is going off, a massive star dying, collapsing, forming a neutron star in the violence of its death, flinging its outer layers into space. All of it is happening right now. All of it has been happening since long before humans existed to watch it. And all of it will continue on its vast timescales long after we are gone. But for a brief moment in the history of the universe, for the past 57 years, since a young woman in a Cambridge field heard the heartbeat of a dead star, we have been paying attention. The physics is unfinished. The questions are open. The instruments are being built. The universe is vast. The mysteries are endless. The journey continues.